Hello everyone and welcome back. In this video we're going to talk about an application of implicit differentiation. Now let's suppose that we wanted to calculate the derivative of a complicated function such as y equals x to the 3/4 times e to the 3x over tan squared times 3x plus 2 to the power of 4. Now in order to find the derivative, we would need to use many of our differentiation rules that we've learned in this chapter. However, we can simplify our calculations by taking logarithms first. And this method is called logarithmic differentiation. Now the first step in logarithmic differentiation is to take the natural logarithms on both sides of the equation y equals f of x. Now why do we want to take the natural logarithm rather than any other logarithm? Well, that's because the derivative of the natural logarithm is more simpler than the derivative of logarithms with any other base. Then we want to use the laws of logarithms in such a way that simplifies the expression so that it's easier for the second step. The second step is to differentiate implicitly with respect to x, and the third step is to solve the resulting equation for dy over dx, or the derivative. Now this method is particularly useful for finding derivatives which take the form of y equals f of x raised to the power of g of x, where we cannot use our previous differentiation rules to find its derivative. So let's take a look at a few examples of logarithmic differentiation. So let's find the derivative of this function. So the first step is to take the logarithm on both sides of the equation. So we have the natural log of y is equal to the natural log of x to the 3/4 times e to the 3x divided by tan squared x times 3x plus 2 to the power of 4. So next we want to simplify the right-hand side of the equation by using the laws of logarithms. So if we have a product within the logarithm, then we can simplify by writing it as the sum of logarithms. And if we have a quotient within a logarithm, then we can simplify by subtracting the logarithms. So we'll use the first and the second properties to simplify the expression. So we have x to the 3/4 times e to the 3x. So using the first law, we get x to the 3/4 plus the logarithm of e to the 3x. Now quotients can be written as the difference of the logs. So since we have tan squared x in the denominator, this becomes minus the tangent, or minus the logarithm of tan squared. And we also have the 3x plus 2 to the power of 4 in the denominator. So this will also be minus the ln of 3x plus 2 to the power of 4. So next we can use the third law to simplify powers within the logarithm. If we have a power inside of the logarithm, then this can be multiplied in front of the log. So using the third property, we have an exponent of 3/4 on x. So this becomes 3/4 times the natural log of x by using the third property. And similarly, we have plus 3x times the ln of e minus, there's an exponent of 2 on tangents, so this is 2 the natural log of tan And we have an exponent of 4 on the last term. So we have minus 4 times the logarithm of 3x plus 2. So now that we've simplified the right-hand side of the equation, we can now use implicit differentiation. So we're going to take the derivative of both sides with respect to x. So on the left-hand side, we have the derivative of the natural log of y is equal to the derivative with respect to x of the right-hand side. So we have 3/4 times the natural log of x plus 3x. And now the natural log of e can be simplified to 1. So it's 3x times 1, which is just 3x. Then we have minus 2 times the natural log of tangent of x minus 4 times the natural log of 3x plus 2. So on the left-hand side, we have the derivative of the natural log of y with respect to x. So we'll use the chain rule. So we'll differentiate with respect to y. So the derivative of the natural log of y is 1 over y and then we multiply by dy over dx. So that's the derivative of the natural log of y with respect to x. And on the right-hand side, the derivative of 3/4 times the natural log of x with respect to x is 3/4 times 1 over x plus, now the derivative of 3x with respect to x is 3. Then we have minus 2 times the derivative of the natural log of tangent. So here we use the chain rule. So we first deal with the natural logarithm. So the derivative of the natural log is 1 over and we keep the inner function unchanged, which is the tangent of x. And then we multiply by the derivative of the inner function. And the derivative of tangent is secant squared. So this is multiplied by the secant squared of x. And then we have minus 4 times the derivative of the ln of 3x plus 2. So again, we use a chain rule. So the derivative of the natural logarithm is 1 over the inner function, which is 3x plus 2. And then by the chain rule, we multiply by the derivative of 3x plus 2, which is 3. So now let's simplify the right-hand side. So on the left, we have 1 over y times dy over dx is equal to 3 over 4x plus 3 minus 2 times secant squared x over the tan of x minus 12 over 3x plus 2. So now we'll solve for dy over dx. So we multiply both sides by y. And so we end up with the derivative dy over dx is equal to y times 3 over 4x plus 3 minus 2 secant squared x over tangent of x minus 12 over 3x plus 2. Now if we look at our original function, we have an explicit function, and so our derivative should also be explicit. Well, we know that y is the original function. It's equal to x to the 3/4 times e to the 3x over tan squared x times 3x plus 2 to the 4. So we can replace y with the original function so that our derivative is now explicit. So we have dy over dx is equal to x to the 3/4 times e to the 3x over tan squared x times 3x plus 2 to the power of 4, and this is all multiplied by what's inside of the square brackets. And so this is our derivative. So now let's look at the next function, y is equal to x to the power of x. Note that this is not a power function because the exponent is not a constant, and it's not an exponential function because the base is not a constant. And so we can't use any of the derivative rules that we have learned in order to find the derivative of x to the power of x. And so here we will use logarithmic differentiation to find dy over dx. So the first step is to take the natural log of both sides. So we have the natural log of y is equal to the natural log of x to the power of x. And now we will use the third law of logarithms to simplify the right-hand side. So the exponent of x can be multiplied in front. So we have x times the natural log of x on the right-hand side. So now we can use implicit differentiation to find the derivative on both sides of the equation. So the derivative of the ln of y with respect to x, by the chain rule, that's 1 over y times dy over dx. And on the right-hand side, we will use the product rule. So the derivative of f is 1 times g, which is the natural log of x, plus f times the derivative of g. So the derivative of the ln of x is 1 over x. And so we can simplify this to 1 over y dy over dx is equal to the natural log of x plus 1. So now let's solve for y. We'll multiply both sides by y. And because our original function was explicit, then the derivative should also be explicit. So we'll replace y with the original function, which is x to the power of x. And so the derivative is x to the power of x times the natural log of x plus 1. So now let's look at more examples of using logarithmic differentiation. So here we have y equals the root of x minus 1 over x to the 4 plus 1. We know that the square root can be written as an exponent. So this is x minus 1 over x to the 4 plus 1 raised to the power of 1/2. So let's use logarithmic differentiation. So we take the log of both sides. And then we'll use the laws of logarithm to simplify the right-hand side. So the exponent of 1/2 can be multiplied in front. So we have 1/2 times the ln of x minus 1 all over x to the 4 plus 1. And then we'll use the second logarithm to rewrite the ln of x minus 1 over x to the 4 plus 1 as the ln of x minus 1 minus the ln of x to the 4 plus 1. And notice that the 1/2 will distribute to both of the logarithms. So we have the ln of y is 1/2 times the ln of x minus 1 minus 1/2 times the ln of x to the 4 plus 1. So now we'll differentiate both sides with respect to x. So on the left-hand side, we have 1 over y times dy over dx. And on the right-hand side, we have 1/2 times the derivative of x minus 1. So here we have the chain rule. This is 1 over x minus 1 times the derivative of x minus 1, which is 1. Then minus 1/2 times the derivative of ln x to the 4 plus 1. So here we use the chain rule. This is 1 over x to the 4 plus 1 times the derivative of x to the 4 plus 1, which is 4x cubed. So let's simplify the right-hand side. We have 1 over 2 times x minus 1 minus 2x cubed over x to the 4 plus 1. So the 4 over 2 can be reduced to 2 over 1. So now we'll multiply both sides by y, and we can also replace y with the original function. So the original function was the square root of x minus 1 over x to the 4 plus 1. So this was equal to y, and this is multiplied by 1 over 2 times x minus 1 minus 2x cubed over x to the 4 plus 1 and this is our derivative. In the next example, we have y equals cos x to the power of x. Again, this is in the form f of x to the power of g of x. So we need to use logarithmic differentiation to find the derivative. So we have the ln of y is equal to the ln of cos x to the power of x. So the third law, we will multiply the exponent of x in front of the logarithm. So that's x times the natural log of cos. And now we can use implicit differentiation. So we'll find the derivative with respect to x on both sides. So on the left-hand side, we have 1 over y times dy over dx is equal to, now the derivative of x times the ln of cos, we will use the chain rule. So we'll let x be f and the ln of cos be g. So f prime times g, that's 1 times the natural log of cos plus f times g prime. So the derivative of g, we will use the chain rule. So the derivative of the natural logarithm is 1 over the inner function, which is cos. And then we multiply by the derivative of cos, which is negative sine. So let's simplify the right-hand side. We have the natural log of cos minus x times sine over cos, which is also equal to the tangent of x. So now we'll multiply both sides by y and replace y with the original function. So dy over dx is equal to cos of x to the power of x times the natural log of cos minus x times the tangent of x. And this is our derivative. So our next example is y equals e to the negative x times cos squared x all over x squared plus x plus 1. So let's use logarithmic differentiation. So we have the natural log of y is equal to the natural log of e to the negative x cos squared of x all over x squared plus x plus 1. So using the first and second laws, we have the natural log of e to the negative x plus the natural log of cos squared x minus the natural log of x squared plus x plus 1. And then we'll use the third law to rewrite exponents and multiply them in front of the logarithms. So for the first term, we have an exponent of negative x, so that's negative x times the natural log of e. For the second term, we have an exponent of 2, so that's plus 2 times the natural log of cos. And then we have the third term, which is the natural log of x squared plus x plus 1. And again, the natural log of e can be simplified to 1. So now let's take the derivative of both sides with respect to x. So on the left-hand side, we have 1 over y times dy over dx is equal to negative 1 plus 2 times the derivative of the ln of cos, which is 1 over cos times negative sine plus the derivative of ln x squared plus x plus 1, which is 1 over x squared plus x plus 1 multiplied by the derivative of x squared plus x plus 1, which is 2x plus 1. So let's simplify the right-hand side. We have 1 over y dy over dx is equal to negative 1 minus 2 tangent of x plus 2x plus 1 all over x squared plus x plus 1. So then we'll solve for dy over dx. So we'll multiply both sides by y. And then replace y with the original function. So we have dy over dx is equal to e to the negative x cos squared of x over x squared plus x plus 1, and this is all multiplied by negative 1 plus or minus 2 tan of x plus 2x plus 1 over x squared plus x plus 1. Alright, let's look at the next example. We have y equals the root of x times e to the negative x squared minus x times x plus 1 to the 2/3. So let's use logarithmic differentiation. So we have the ln of y is equal to the ln of, let's rewrite the root of x as x to the 1/2 times e to the negative x squared minus x times x plus 1 to the 2/3. So now let's simplify by writing this as the ln of x to the 1/2 plus the ln of e to the negative x squared minus x plus the ln of x plus 1 to the 2/3. And so now let's multiply the exponents in front of the logarithm. We have 1/2 times the ln of x minus negative x squared minus x times the natural log of e plus 2/3 times the natural log of x plus 1. And we know that the ln of e is equal to 1. And now we'll use implicit differentiation. So the derivative on both sides with respect to x. So on the left-hand side, we have 1 over y times dy over dx is equal to 1/2 times the derivative of the ln of x, which is 1 over x, minus the derivative of x squared, which is 2x, minus the derivative of x, which is 1, plus 2/3 times the derivative of ln x plus 1, which is 1 over x plus 1 times 1. So now multiplying both sides by y and replacing y with the original function, we get dy over dx is equal to the root of x times e to the negative x squared minus x times x plus 1 to the 2/3 multiplied by 1 over 2x minus 2x minus 1 plus 2 over 3 times x plus 1. And this is our derivative. So now let's look at y equals the sine of x to the power of the ln of x. So let's use logarithmic differentiation. So we have the ln of y is equal to the ln of sine x to the ln of x. So using the laws, we will multiply the ln of x in front of the logarithm. So that's ln of x times the ln of sine of x. And then we'll use implicit differentiation. So on the right hand side, we'll use the product rule. So the ln of x will be f, the ln of sine will be g. So on the left hand side, we have 1 over y times dy over dx, which is equal to f prime, which is 1 over x, times g, which is the ln of sine of x, plus the ln of x times the derivative of ln of sine, which is 1 over sine times cos. So let's simplify. We have the ln of sine all over x plus the ln of x times cos over sine, which is cotangent. So now we'll multiply both sides by y and then replace y with our original function. So that gives us dy over dx is equal to the sine of x to the ln of x times the ln of sine all over x plus the ln of x times cotangent of x. And this is our derivative. So next we'll look at y equals the tangent of x to the power of 1 over x. So once again, we'll use logarithmic differentiation. We have the ln of y is equal to the ln of tangent of x to the 1 over x. So the ln of y is equal to 1 over x times the ln of tangent of x, which is the ln of tan all over x. And now we'll differentiate both sides with respect to x. We have the derivative of ln of y is equal to the derivative of the ln of tan all over x. So on the right hand side, we'll use the quotient rule. Our f will be the ln of tan, and our g will be x. So on the left hand side, we have 1 over y times dy over dx is equal to f prime, which is 1 over tan times secant squared times g minus the ln of tangent times the derivative of g, which is 1, and this is all over g squared. So we have 1 over y times dy over dx is equal to x times secant squared x all over tan minus the ln of tan and this is all over x squared. So now we'll multiply both sides by y. And then replace y with the original function. So we have dy over dx is equal to the tan of x to the 1 over x, and that's all multiplied by x secant squared x minus the ln of tan x, and the x secant squared x is over tangent, and this is all over x squared. And this is our derivative. So I'll leave the last two examples as an exercise, and this will conclude our lesson for this video. In the next video, we will talk about some practical applications of implicit differentiation, which are on rates of change and related rates. And I'll see you then.